Starting in the early 2000s, vehicles started becoming far more complex with the introduction of hybrid powertrains. Vehicles with many different architectures and degrees of hybridization were released to the market that are still being manufactured today. These include micro-hybrids, integrated starter alternator hybrids, and full hybrids, such as the power split used by the Toyota Prius. But there are many other different architectures, such as pre-transmission hybrids or series architectures, series parallel architectures. So there are many different types of powertrain architectures because there's many different places that you could couple a motor to a drive shaft, and there are many places that you can integrate a electric machine within a transmission, and the number of electric machines might vary. So you might have it with the engine, you might have it before the transmission, you might have a motor after the transmission, you might have motors connected to the wheels or many other places within the powertrain. So there are many options in terms of hybrid architectures. And then you can also add other technologies to that. So, in the teens, as battery technology had matured enough, plug-in hybrid vehicles started becoming popular, where you had the option of charging the vehicle and having an all-electric range. And then after the introduction of plug-in hybrid vehicles, battery technology continued to improve, and then we started seeing fully electric vehicles coming to the market. So these vehicles had ranges within the range or within the reason in which consumers would accept. And then finally, in the late teens and the early 2020s, connected and automated vehicle technologies began being deployed. These technologies included vehicles with different levels of automated driving or automation. And then also you'd start to see the introduction of vehicle to vehicle communication, vehicle to infrastructure communication, in which the vehicle might receive information from the traffic lights so that it can know when a traffic light is going to change color, so you can implement strategies such as eco approach. So over the last 20 years, transportation has become far more complex with the advent of all these different technologies, both on the powertrain level and the vehicle level, but also now the intelligence that's being added to vehicles and the intelligence that's being added to roadways. So because of that, that drives this need or the necessity to have new types of tools that are able to answer questions. So originally you could evaluate a vehicle on certification cycles, so a city or highway cycle, and get a good idea of the fuel economy for the vehicle and what potential energy savings there would be in the future. But now you have to simulate an entire urban area to get an idea of what impact some of these new technologies will have. So you can ask questions such as what fuel economy and energy savings is possible with connected and automated vehicles. And then you can ask that question as the level of automation changes. So if you have level 1 automation versus level 2 all the way up to level 5, that's going to change the traffic flow in an entire urban area, as you see on the right. And there are tools that are able to simulate that very well. And then you could also focus on smaller areas within a city. So you could focus in on a small corridor and look at what impact V to V or V to I would have in those areas. And you could ask questions, what if 1% of those vehicles were fully automated, what impact would that have on traffic flow? Is there a point at which you have enough automated vehicles that you're able to smooth out the traffic flow and change the way the vehicles are driven? And those all reflect and have impacts on the individual vehicle. What's important, though, is if you really want to answer the question, if you have this question, well, what impact does it have on the vehicle? What's your fuel savings? Well, that depends on the type of the vehicle. So in the past, you would maybe be able to get by, or you could get by with rough estimates of fuel economy and just say, okay, if you know the speed of the vehicle has changed by X amount, then that must mean that the fuel economy changes by X amount. But now with the diversity of different vehicles on the roadway, where you have a mix of conventional vehicles, plug-in hybrid vehicles, and electric vehicles of different types, that's a far more complicated question. So you need a tool such as Autonomy Express that has that level of fidelity that's able to, add to and answer those questions. So you could get mesoscopic traffic simulation results, and you could also get those microscopic traffic simulation results across a corridor. So mesoscopic is where you're taking it across an entire city. Microscopic is where you're getting it within a small network of roads or a corridor. And they're tools that are very good at producing the average traffic speed, the traffic density, and are able to generate those results. So the question though becomes, those tools are very adept at doing that, but you still need to create fuel economy. You still need to create energy consumption. And to do that though, you need a tool, and that's where Autonomy Express comes in. So Autonomy Express is able to take the results of a traffic simulation tool such as POLARIS, or microscopic traffic simulation tools such as AimSun, VISSIM, and SUMO, and is able to take the results of those simulation tools and make very accurate energy predictions on those vehicles. And it's able to do it quickly too. That's the other aspect of it, because you're generating, in some cases, millions of drive cycles. So you want to be able to make predictions as fast as possible. And that's what Autonomy Express allows us to do across many different vehicle types. So HEVs, PHEVs, BEVs, even fuel cell hybrid vehicles. And the big advantage of Autonomy Express that allows it to do this and allows it to do it accurately is that it has predefined vehicles, and it has thousands of vehicles, and it covers a wide range of time frames. So you can see that you have vehicles from the past all the way into the future to 2050. You have vehicle types such as from light duty all the way to heavy duty. And then you have many different powertrain types, many of which I've mentioned. You have conventional, HEV, PHEV, electric fuel cell. You have all sorts of different fuel types. So you have your diesel and gasoline, but you also have biofuels and natural gas and even hydrogen. And then you have technology. So you have an uncertainty in the technology. So there's certain assumptions being made in terms of how efficiency of components will improve. And that's where the technology cases come in. So if you have an optimistic case where you have a lot of technology improvement, that's your high case. If you have a more business as usual where there isn't as aggressive improvements in technology, you have your low case. And that allows the prediction of energy consumption, GHGs, with the tool Autonomy Express. So what you're doing is you're able to take Autonomy Express and add to something that has never been possible before, where you're adding high fidelity vehicle level energy consumption predictions to traffic flow and micro simulation flow simulations. Okay, what I'll do next then is start Autonomy Express. So I'll do that by launching Amber 2024. So Autonomy Express is an application that lives within Amber. Amber is the advanced model-based engineering resource. It's a tool that has different applications that live within it and allows us to deploy different tools to end users that include, model-based systems engineering applications. So Autonomy Express is one of these applications. And it has a workflow, so I could go to the Autonomy Express workflow. And that will load. And you can see here, there are the different input file types that Autonomy Express can take. So it could take time-based cycles. So there's some options here for time-based cycles where you have vehicle speed versus time. But it could also take input that is formatted from the SUMO microsimulation tool or the VISSIM microsimulation tool. It could take input from POLARIS, which is a mesoscopic traffic simulation tool, which models the traffic in an entire city. And then there's AimSun, which is another microsimulation tool. So if we have VISSIM selected here, the information that appears below it, basically the information that allows one to convert the file type into a Autonomy Express compatible file type. So what we want to do is then select the VISSIM example file, which is a CSV file. So I go here and then I go to example VISSIM output file, and I select the CSV file and I click open. So now we've selected a output from VISSIM. And then what we'll do next is we go to trip assignment. So trip assignment, in here you select the library of vehicles. So there's a selection of vehicles that has been chosen, and there are 5,000 vehicles total that are compatible with Autonomy Express. And the information about each vehicle, so we have the actual compiled executables that run or represent the high fidelity model of each vehicle, but then there's also some metadata that goes along with it, which is stored in also a CSV file. And here is just a small selection of the vehicles that are available. So just to sort of run quickly, we have a compact, an electric vehicle with a 100-mile range, a hybrid electric vehicle with an integrated starter generator. Then there's a fuel cell hybrid vehicle and a power split hybrid vehicle. And then there's even a PHEV that's present here. Then there's some extra tags that describe in a little bit more detail the class of the vehicle, if it's compact or mid-size, the type, which would be light duty, the powertrain, so conventional, BEV, ISG, integrated starter generator, fuel cell, hybrid electric vehicle, plug-in hybrid electric vehicle, and then the fuel type, gasoline, electric, hydrogen, and then the level of automation. So there's some of this extra information that comes along in the CSV file. There's trip export. So when the simulation runs, you could decide where you want the output results and then which output results you would like to see. So you have, fuel consumption and electrical consumption. You have driving distance, and then there's other emission options which are produced. Then if you go to trip run, it's here that you actually have the some of the other options of where you want to run. There's connections to other applications such as GREET, which produces well-to-wheel emissions for each vehicle type. So we connect to that application. And then once you set up your assumptions here, you can click run, and then the simulations will run. And one nice thing about it is it's already configured so that if you have, say, a cluster with the MATLAB job scheduler, if you hit run and everything's configured, you have the parallel computing toolbox on your local machine, it will run those simulations in parallel. So I click run, and it will launch MATLAB, and then it will run those simulations. Okay, now you can see that the results have loaded. You can see the different charts that are created. Here's some of the default charts. So you have fuel consumption in kilograms and electrical consumption on the right here in joules, so that those are total values. Here we have average fuel consumption in kilometers per liter based on the vehicle class, so it's just giving you some aggregates. So these are the models that were actually run. So this is an average for those vehicles on all the trips that the vehicles ran on. One thing to remember is with the trip assignment, what you're doing here is you're assigning vehicles to trips, the VISSIM trips. And the way I have it selected here is it's assigning those vehicles to each one of those cycles. So it runs every vehicle on every one of the trips in the VISSIM file. So these averages in the results are across all those trips. And then there's also average emissions for each one of those vehicles across all the trips. If we go to the next tab, we have the data view here. So we have some of the trips. So each trip receives a trip ID. And then you have each characteristics that's being computed by the model. So you have fuel consumption in mile per kilogram, and then you have electrical consumption, the distance driven in miles, fuel consumption in kilometers per liter, and then the GHG gases and other criteria pollutants that are produced. And then you have the average and minimum values that are also produced here. You can go to the pivot table. So in the pivot table, what you can do is plot. You have a list of labels. So what I could do is I could say, okay, we have a trip ID. So we assign the trip ID to the rows. We could assign the vehicle name to the columns. And then we could choose a value for each one. So we could look at the greenhouse gas emissions and drop it here for measure. And then we could expand it. So we could expand it per row, and then we could expand it per column. And then we could see for each trip the vehicle and then the value that it produced for each one of these. So because it's using well-to-wheel values for GREET, even the electric vehicle is producing some greenhouse gas emissions, because that is the greenhouse gas emissions that's created by the manufacture, the production of the electricity. So then we can go to some of the other plots. There's this data chart here, and it has various values that you can add. You can group them by trip ID, or you could group it by vehicle name. And there's various values that you can add here in terms of different pollutants or greenhouse gas or the fuel consumption. You can choose the plot type too if you wanted a line graph, or you want it to be columns, which is what we had before. So there's various options here that you could use to view values. And then finally, there's this box chart that shows the various parameters that we have here. So we could show the GHG parameters, or we can show the fuel consumption here in kilograms, and that's showing it for each one of the trips that I have here. And it's showing a max and a min value, and then it's showing an average value. Or you can group it by vehicle name, so you can also see it per vehicle name. So that's the other way that you can view it. So you get max, min, and an average, and then the quartile values that are shown there. So that gives a good overview of what sort of a basic introduction to Autonomy Express and what Autonomy Express is capable of doing. So you can take your traffic flow simulation, such as output from Polaris, or you could take your output from a tool such as VISSIM or AimSun or SUMO, and then take the results of a micro simulation run, get the traffic flow from that micro simulation run, and then run it through Autonomy Express. So here we just did a very small subset of results and a small subset of the processing that you can do to just kind of get a feel and an introduction of what the tool is capable of. But this is a great way to add high fidelity energy predictions to your traffic flow results.